Hello, my name is Michelle Brianes Baños, and today I will present my work on the development of flame-retardant cotton fabric using zinc oxide nanoparticles. Cotton is one of the most widely used natural fibers due to its comfort and breathability. However, it is also highly flammable, which limits its use in safety-critical applications. At the same time, semiconducting oxides such as zinc oxide offer functionalities including ultraviolet protection, antimicrobial activity, and thermal stability. This motivated the exploration of zinc oxide as a flame-retardant additive for cotton, with chitosan used as biopolymer matrix. The main goal of this project was to develop coatings for cotton fabrics that improve their thermal and flammability behavior. Specifically, the objectives were to synthesize zinc oxide nanoparticles, apply chitosan zinc oxide coatings to cotton at different nanoparticle loadings, and characterize the treated fabrics using thermal, spectroscopic, and flammability tests. So, first, zinc oxide nanoparticles were synthesized by a precipitation method. Sodium hydroxide was dissolved in water and ethanol, and this solution was added drop by drop to a zinc acetate solution under stirring at 55 degrees Celsius for 2 hours and 15 minutes. The solution turned white and was allowed to cool to room temperature. It was then centrifuged at 15,000 revolutions per minute at 4 degrees Celsius for 35 minutes. The precipitate was washed with ethanol and centrifuged again for 5 minutes. Finally, the precipitate was collected and calcined at 60 degrees Celsius for 3 hours. In this way, zinc oxide nanoparticles were obtained as a white powder. Next, the cotton fabrics were treated. The desired amount of zinc oxide nanoparticles was stirred with a 1% acetic acid solution. Then 1 gram of chitosan was slowly added at 900 revolutions per minute for 10 minutes. The mixture was homogenized in an ultrasonic bath for 30 minutes, and cotton fabric samples were then submerged in the mixture for 50 minutes. Then it was laid flat over wax paper and passed through a roller to remove excess liquid. The fabric was dried at 80 degrees Celsius for 10 minutes and cured at 100 degrees Celsius for 5 minutes. In this way, treated cotton fabrics were obtained, and 5 different samples were prepared. One untreated fabric, which is our blank, one fabric treated only with chitosan, which is our sample 0. The sample 1 is chitosan and 0.1 weight% zinc oxide nanoparticles. Sample 2 is chitosan and 0.5 weight% zinc oxide nanoparticles. And sample 3, which is chitosan and 0.9 weight% zinc oxide nanoparticles. And for characterizations, Raman spectroscopy was used to confirm the presence of wurtzite zinc oxide and to detect possible interactions with chitosan. The thermogravimetric analysis was performed to evaluate the thermal stability of the samples. And finally, a vertical flame was conducted to study the flame resistance and afterglow behavior. In this test, a 12 inches by 3 inches sample was subjected to a methane flame for 12 seconds. 3 parameters were recorded. One was the duration of the visible flame after removal from the fire. Another is the duration of the afterglow, which is the slow burning of the fabric, and the char length of the sample after self-extinguishing. And for the results, the Raman spectra showed the characteristic band of zinc oxide at 440 inverse centimeters, confirming its presence. Additionally, shifts and changes in intensity were observed in the carbon-oxygen-carbon band and other chitosan-related peaks, suggesting interactions between zinc oxide and chitosan rather than simple physical mixture. For the thermogravimetric analysis, the thermal analysis revealed that zinc oxide improved the thermal stability of cotton. The most significant effect was observed at the highest zinc oxide loading, around 0.9 weight%, which shifted the main decomposition temperature by approximately 30 degrees Celsius compared to the blank fabric. This indicates that zinc oxide nanoparticles help delay cotton degradation under heat. And for the flame tests, all fabrics were ultimately consumed. However, the flame behavior strongly depended on zinc oxide content. The sample with 0.1 weight% zinc oxide showed the longest afterglow, lasting about 50 minutes and 56 seconds, and a partial suppression of the flame compared with the blank and chitosan-only samples. Higher loadings also modify the burning behavior, but different after flame and afterglow characteristics. For example, sample 2 performs similarly to sample 0, which is only chitosan, and sample 3 performs similarly to sample 1. So these results confirm that zinc oxide does influence the combustion pathway of cotton, even at very low concentrations. And in summary, the chitosan zinc oxide coatings were successfully applied to cotton without altering its appearance. Raman confirmed the presence of zinc oxide and suggested chemical interactions with chitosan. Thermogravimetric analysis demonstrated improved thermal stability, particularly at 0.9 weight%. Empirical flame tests revealed that zinc oxide content modulates after flame and afterglow, with 0.1% showing the most distinctive effect. Overall, this work demonstrates that combining a natural polymer like chitosan with zinc oxide nanoparticles can be an environmentally friendly strategy to enhance fiber performance in cotton textiles. Although the fabrics were ultimately consumed, the modified combustion behavior and improved thermal resistance suggest a pathway toward safer and more sustainable textile materials. Thank you for your attention.